Hello and welcome. I'm Taylan Özden from the Technical University of Darmstadt. And today I'm going to talk about ElastiSim, our batch system simulator for malleable workloads. Let's start with a refresher on resource and job management first. So resource and job management systems, also very often called job schedulers or simply batch systems, they're responsible for scheduling jobs and providing resources in large-scale computing environments such as HPCs, clouds, or grids. And depending on the objective, batch systems aim to maximize system efficiency, that would be the system perspective, or to minimize job completion times, that would be more the user perspective. And the scheduling algorithms where these decisions are taken are key components to improve system performance. So before we dive into the details, let's classify jobs first. So Feidelson and Rudolph proposed 4 different job categories, and it essentially boils down to who or which entity decides about the number of assigned resources at which time. So if the user decides about the number of resources at submission time, we speak of rigid jobs. This is also the most common type in HPCs. If the system is able to assign a variable number of resources at the beginning of a job, then we speak of moldable jobs. If the user, or rather in that case the job, is able to request a different number of resources at runtime, then we speak of evolving jobs. And if the system is able to make resource changes during runtime, then we speak of malleable jobs. You will also very often see that evolving and malleable jobs are classified as adaptive jobs in the literature. So here you can also see a figure describing the different job types. On the left side, you can see rigid jobs, which have a fixed number of resources throughout its execution time. In the center, you can see moldable jobs, where in the beginning of the job, the system is able to assign a variable number of resources, and adaptive jobs, which are able to reconfigure their resources during runtime. So if we now want to evaluate scheduling policies, we could experiment on a real system. But usually experiments on real systems are expensive, time-consuming, very resource-intensive. They might introduce system threats, so not every administrator will allow that, or almost none. And of course, it might not be available to everyone because not everyone has access to a large-scale computing environment. So usually you can rely on simulations. They are fast, reproducible, independent. You can apply variable constraints like a different system topology, and usually they are very resource efficient. Okay, so here are some batch system simulators and how they compare to ElastiSim. So we have simulators such as ACASIM, ELEA, or BATSIM, and usually they do not have to, but usually they are based on platform simulation frameworks like GridSim or SimGrid. Most of these simulators, they also do support the standard workload format, the SWF. BATSIM, for example, also has a customized way of defining workloads as we do. We do not support the standard workload format currently, as it is inherently rigid, and our main focus is still, of course, malleability. And but we also support language-independent interfaces for scheduling algorithms to integrate custom scheduling algorithms. We have a GPU support. And of course, the main focus, we support malleable workloads that are augmented with performance models, which I will explain in a few moments. So, but first, let's come to workload modeling. So why do we need workload modeling? Well, the reliability of any simulation will always depend highly on the executed workload in the simulated environment. So that means that if you do not have a representative workload, you will not get any meaningful results. What we did is we studied workload characterizations, and most of these characterizations, they indicate that workloads tend to alternate between different phases, like compute-intensive phases and I/O-intensive phases, for example. And what we do is we propose a workload model that comprises jobs and so-called application models. Okay, so here you can see our proposed workload structure. On the very top, you can see a set of jobs, which constitutes the workload, the simulation scenario, and each job holds certain properties. You can also see that each job has a so-called application model, and staying on the right side of the figure, the application model comprises multiple phases, and each phase can hold multiple tasks. So while phases are an organizational structure, tasks are low-level activities such as computation tasks or I/O tasks. So, but we do not only have the main phases, we also have optional phases like an initialization phase, for example. This is a phase that is only executed once at the very beginning, at the first configuration of a job. And then we have a reconfiguration and an expansion phase. So for malleable jobs, if you have a resource reconfiguration, chances are that you introduce some kind of overhead. For example, that might be due to data redistribution, or that might be something like reading a model from the parallel file system again. So what we do is we call that reconfiguration penalty, and we have a reconfiguration phase that is after reconfiguration has taken place, that is executed on all resources, or an expansion phase that is only executed on newly allocated resources. And each of these phases, they hold multiple tasks, and for malleability reasons, these tasks, they can be described, or their payload can be described by using performance models. So let us introduce performance models first. So what are performance models? Performance models are simply human-readable mathematical functions, and we use them to allow the application to adapt to resource configurations or resource reconfigurations. So usually you can obtain performance models by inspecting the application, maybe the source code, or you can use tools like XtraP to get an empirical analysis of real runs of the application. So, for example, if we have a simple performance model like floating point operations divided by the number of compute nodes, this would be a very simple performance model, and the speed up would look something like this. So you see, that might not be very realistic. So what you want to do is you might want to introduce some nonlinearity, for example. So floating point operations divided by the number of compute nodes to the power of 0.85. So, and then you can introduce some nonlinearity into your speedup, which might reflect reality a little bit better. Of course, you can also describe applications using Amdahl's law by having a parallelizable and a non-parallelizable part. All these possibilities are given to you by using performance models in your tasks. Which brings me to the application execution model. So if you have a look at the upper left, you can see that we support multiple task types such as CPU, GPU, I/O, or delay tasks. And all of these tasks, they hold a certain payload. The payload describes the amount of work that is executed on the simulated platform. So for CPU tasks, that is, for example, the number of floating point operations, and for I/O tasks, that might be the number of bytes to write to the parallel file system. And as we describe them using a single number or a performance model that is evaluated to a single number during runtime, we somehow have to distribute this number among the participating resources. And this is where we use payload distribution patterns. So using payload distribution patterns, we can describe how the work will be divided among the participating resources. So for computational tasks, that might be, for example, every rank is participating in the task, or that might be something only the root rank is doing the work. And for communication tasks, that might be a pattern like everyone is communicating with everyone, so a classic all-to-all pattern, a ring pattern, or following a master worker paradigm. So And during the execution, which you can see on the bottom, you see that we have, in this case, as an example, multiple phases, 3 phases, and they're all executed consecutively. And for malleable jobs, you can see that between those phases, we introduce so-called scheduling points. These are the points where an application is able to accept a resource reconfiguration that was issued by the scheduler before. Okay, so here you can see the architecture of ElastiSim. So speaking of a black box first, you as the user, you have to provide the platform, the workload, and the configuration, as well as the scheduling algorithm. And what you get after the simulation has terminated is you will see the simulation results and outputs. On the bottom, you can see that we have the main simulation process. And what's happening during the simulation is that your scheduling algorithm is in constant communication with the simulation process. So every decision the scheduling algorithm takes is forwarded to the simulation process and then applied on the simulated platform, so that then you can see how it affected the behavior of the platform in the simulation results and outputs. So the simulation process consists of 2 different parts. So first of all, the simulation engine based on a SimGrid core. We use, of course, SimGrid entities like the CPU or network links. And of course, we have extended SimGrid by own entities such as the GPU or burst buffer semantics, which you can see in bold text here. And as with all discrete event simulators, you have multiple actors in the system. So we have, for example, the job submitter, which takes the role of the user submitting jobs. We have the batch system, of course. Then the compute node, which is not only a resource, but also an actor, which is in constant communication with the batch system. And of course, we have the monitoring module that is monitoring the system to write the simulation outputs in the end of the simulation. Here you can see the different actors and how they interact with each other. On the very left, you can see the job submitter reading the workload file, simulating user behavior by submitting jobs to the batch system. The batch system is invoking the scheduling algorithm. The scheduling algorithm receives the state, sends back a schedule, and after receiving the schedule, the batch system will manage the platform by assigning nodes to jobs. So every node also reports its state to the batch system, so that the scheduling algorithm is always aware of the state of the nodes. And we have the monitoring module observing the platform and writing the utilization files. So how the batch system interacts with the scheduling algorithm is defined in the scheduling protocol. As of now, the scheduling algorithm in ElastiSim is invoked periodically in an interval that the user specifies in the configuration file. Also, if specified, the invocation can also take place on job submissions or job completions, for example. In each invocation, the scheduling algorithm will see the job queue, the state of each compute node, and if required, system metrics such as the I/O utilization, for example. What we also support is that each job is reporting its progress. So as we have a strict hierarchical structure of phases, this progress is defined by the number of completed and the total number of phases. So this will also allow the user to create progress-aware scheduling algorithms, for example. Coming to the storage system, we provide semantics for 2 different types of storage systems in ElastiSim: parallel file systems and node local burst buffers. So as for parallel file systems, we model them as dedicated I/O nodes behind a single namespace, so that when jobs are executing an I/O task, they will automatically target the I/O nodes that are part of the parallel file system. But we also allow users to create affinities to certain I/O nodes. As for node local burst buffers, they come in 2 different flavors: exclusive access and wide striped access. In exclusive access, the nodes have only access to their own burst buffers, but in wide striped access, the burst buffers of nodes that are allocated to a single job are aggregated behind a single namespace. We also have support for GPUs, and our GPU model consists of multiple GPUs per compute node with a user-specified performance. All GPUs on the nodes are fully connected with a user-specified bandwidth. And what ElastiSim provides is automatic detection of intra and internode communication. If you look at the right side, this is an example where the GPUs are communicating in a ring pattern. And with dashed lines, you can see that these are representing intranode communication, and solid lines, they represent internode communication. If you execute the task, or if the task is executed on the platform, and these GPUs communicate with each other, you don't have to worry about that, because ElastiSim will automatically then distinguish between intra and internode communication, so that you will see that also in the simulation outcome. Okay, so coming to the evaluation. To evaluate ElastiSim, we established two different experiments. The first one to validate our workload and application model, and the second one to assess the applicability of ElastiSim in a large-scale scenario. So for the first experiment, we trained various convolutional neural networks on a GPU cluster, and we modeled the application in ElastiSim, and afterwards compared the real runtime against the simulated runtime. We used the epoch runtimes as a baseline. For the second experiment, we took 400 jobs from the deep learning cluster of Microsoft, Philly, and we then applied various scheduling algorithms to evaluate the results to see if the results are meaningful. Okay, so coming to the epoch runtime comparison, you can see the real training here in blue and the simulated runtimes in orange. We used ResNet as a baseline model, and then used the parameters of MobileNet, VGG16, SqueezeNet, and AlexNet to compare the runtimes to the real models. And what you can see is that for ResNet, MobileNet, and for VGG16, we are very close to the real epoch time. But for SqueezeNet, for example, we have a small overestimation. You can see also an underestimation for AlexNet. But also, if you look closely, and this is quite interesting, when you, in the real runtime, when you go from 1 to 2 nodes for AlexNet, you will see that there is an increase in runtime in the real training. And if you look closely, you can see that this behavior is also reflected in the simulation, which shows that ElastiSim was able to even catch these kind of small details that most probably occurred due to communication overhead. Coming to the second experiment, we applied 6 different scheduling algorithms on the same workload and measured waiting and turnaround times. 4 of these algorithms were able to exploit malleability, 2 of those were not, so they were in a rigid flavor. So what you already can see, for example, for first come, first serve, is that the malleable counterpart will outperform its rigid counterpart. This is also true for shortest job first, as you can see here in that case. And what you can also observe here is the high number of outliers for scheduling algorithms that prefer jobs based on their remaining time, for example, like in shortest remaining time first or shortest job first once again. So you can see that jobs that would have taken longer, they were scheduled at the very end and they had to wait for a very long time, as you can see here, and therefore the turnaround time also increased. So having a look at these Gantt charts where you can see jobs that are running in blue and when they were waiting in the queue in red, you can see that these Gantt charts also validate the results and are also meaningful. So for example, for first come, first serve, you can see a very clear first come, first serve pattern here on the top right. But also if you look at shortest job first, for example, you will see that the outliers we have seen in the slide before are also here. So especially jobs that are taking longer were disregarded in the beginning and therefore had to wait a long time in the queue. And these outliers are very visible here also in the Gantt charts. One further interesting observation is this is malleable dominant resource first. And you can see this algorithm, this is an algorithm that in the beginning of a job, it assigns one node at a time to multiple jobs and expands these jobs later. And this pattern is clearly visible here, where you can see that multiple jobs started their execution at the same time. And that brings me to the end of my talk. So to conclude, ElastiSim is the first batch system simulator that supports malleable workloads. We proposed a workload model augmented with performance models that supports malleability, and also an application execution model that automatically includes scheduling points to support malleability. And we made ElastiSim publicly available on GitHub, so feel free to check out our repositories. And if you have any further questions, feel free to contact me. My email address is on the slide. Thank you very much.